Good morning, everyone. Welcome to another Lowell Observatory Cosmic Coffee. As you can probably see, I am not the usual host, who is Jeff Hall, our fearless observatory director. And my name is Brian Skiff. And so we decided to take over this week and have a little chat from down in the engine room with some of the folks working on research projects at Lowell. I might mention that even though Lowell is not a degree granting institution like a university, we nevertheless have students working with the Lowell staff astronomers from including Northern Arizona University and other schools around the country. And I'd like to introduce to you Lauren Biddle, who is indeed from NAU and who is working with Lisa Prato's group on Tauri stars. And we're going to talk about a little bit about how we think stars form, and also how planets get there and going as well, and how they turn into things like our own solar system. So, so you can say hello, Lauren.
Hello.
And
everyone is having my coffee ready.
Yes. So I thought we'd start this morning by showing our wide field view of the sky that we have of the Taurus star forming region, or at least part of the Taurus star forming region, which is our famous and most well studied area where there's at least low mass stars forming. And this view takes in about a 2-degree field, so several times the size of a full moon, and shows part of the Taurus dark clouds and stars that are lighting up some of those clouds. I like this picture as a big overview of things, because you can see that you can tell from the picture that the clouds are very much in the foreground of the sweep of the background of stars and even galaxies that you can see in the photo. And the clouds in the star forming region are about 400 or 450 light years away. And you can see in this picture that, to me, amongst the interesting things is over on the left hand side, there's a group of stars and a obviously obscured region with stars in the foreground. And then there's this blue thing that seems to be behind the dark cloud. And interestingly, you think that this bright star over on the left would be the thing that's lighting up the dust that's here. But in fact, that star is in the foreground and has its own small little cloud that it's lighting up. But then there's a tiny little faint star that's actually obscured in this line of dark nebulosity just to the lower right of that bright star. And that turns out to be it's a binary star, but also it's a star that's much hotter than, for instance, the sun. It's about twice the temperature of the sun. And it is the thing, it's actually obscured behind the dust cloud, but the geometry is such that it's open to the back, so that it is the blue hot star that's actually shining and causing the cloud here to be bluish. And so it's an interesting setup. So this area has been studied for most of a century now, and we've learned more and more details. And as in much of astronomy, the devil is in the details, and we get this nice view, this contextual view here of the Taurus dark clouds, but then we want to know about these individual stars and what's going on with them. So we start zooming in, and here we asked Lauren to take over and tell us about stuff that she knows about and what she's studying in these very young stars. The other thing to mention is that the star forming region is very young. Typically the stars are only a few million years old at most. So and compared to 4.5 billion years for the age of the sun. So these stars are 1,000 times younger than the sun. And so they are brand new stars. So take it away, Lauren.
What a great introduction. So a lot of the stars that I study in my research are actually included in this image. And it's just really amazing to look at it and see the beauty in it. And these stars come in different morphologies or different shapes and sizes. And we can see those in the next, slide here, where we have up close images of them using the ALMA Observatory. And this is just a suite of, you could say, like a family portrait. All of these stars are the same type, but some are more diffuse. Some have a single ring and some have many rings. The density of some of the gas and dust around the central star isn't necessarily the same as you expand outwards. There are some clumps that you can see in the ring that could be an indication of planet formation. And one of the reasons that these images are so important and so interesting is because it's predicted that the morphology or the shapes and sizes can tell us whether planets are forming around them or not. And so the gaps in the disks, in between the rings, it's predicted that those could actually be carved out by planets that are forming. And so it looks like a lot of these systems are forming planets, and perhaps maybe we still need to detect them. Some of the systems without gaps could still be forming planets. So there could be many routes to create these gaps. Also, there's some research out there suggesting that maybe instead of planets forming these gaps, perhaps there's some sort of like resonances that are occurring from maybe a planet further in or a planet further out. There's some gravitational interactions that can cause resonances that create these rings.
So I guess one thing having to do with these really interesting ALMA images, is that the scale of them is something like the size of our solar system, or even a few times larger than our own solar system.
Oh yeah, certainly. So if we were to say, for example, if we took one of them, say like UZ Tau E, that's the one on the left center column at the top. That one, there's like a little scale down there that says 50 AU, and AU is the distance from the sun to the earth. And so this is 50 times that little line there. And so if we were to place Earth in this system, we wouldn't actually be able to see it in this image because it's so close to the center star that we can't resolve it. It doesn't have enough contrast there. But I mean, regardless, we still get like great detail of the structure of these systems. And another interesting thing is that the structure might be able to tell us what the architecture of the system, like billions of years in the future, when the disk has dissipated, do the rings indicate where planets will exist, I guess, in like an Earth or a solar system type system. Do you have anything else to add, Brian? These are, I mean, there's such.
Well, we have a question from one of the visitors asking which comes first, the gravitational resonance pattern or the protoplanet. And probably there could be a mix of processes involved to produce those resonances, I would guess.
Yeah, that's a great question, and I don't know if there's an answer to that right now. Like you said, Brian, they could be happening simultaneously. It might even be able to happen without, I mean, there's no guarantee that a planet will form anyway. So like, what if these were just resonances and maybe planets aren't forming around these stars? It doesn't require that one comes first if one doesn't happen.
Yeah,
but
I think I see papers talking often about basically the very small processes and whether the planets start forming or even the clumps of dust start forming as little pebbles, basically, and whether you end up with just hot lumps that eventually spiral into the star, or you actually end up with a planet that actually can persists after the disk dissipates.
Yeah, but the leading theory is that that there are planets in these systems, and we're catching them in the process of formation, and they have not yet fallen into their star if they were going to,
or thrown out.
Yes, or ejected. That total rogue planets totally exist. They can. Yeah.
I guess obviously we know that so many old stars, that like our own solar system and other stars where we have with the thousands of known planets, they obviously exist, and so and with some varying sorts of architecture, with big planets or hot Jupiters in very close to the star, and other ones farther away, and so part of the why it's called research is because we don't know exactly how all of this stuff happens, and the details of it.
Exactly.
So we have another question. What kinds of angular velocity do these systems carry compared to that solar system? I think that's where Kepler's laws come in.
Indeed. And except for maybe very close to the star, the very inner edge of the disk where the gas can actually interact with the magnetic field and the magnetic of the star. The star has a very strong magnetic field. It's thousands of times the strength of the sun, and that can weave into the inner edge of the disk and lock it in rotation with the star. And so the star can actually, rather the disk will then modulate the rotation of the star. And I think that in terms of the total angular momentum of the system, that is one of the dominating factors. When the disk dissipates, actually, I know we were talking about angular velocity, but I got into like angular momentum. It's actually a really cool process, because when the disk dissipates, the star eventually will spin up. And think of a figure skater, and the figure skater has their arms out. They're going to spin more slowly. So if we imagine the arms as the disk, and we bring our arms in, that being that the disk is no longer there, the figure skater, or the star in this case, would spin up. And so that's what happens as it is approaching main sequence. And the main sequence is when it's finally hot enough to start fusing hydrogen to helium in its core.
So I think this is that paragraph that you just gave us is probably a good segue into showing us your cartoon version of what we think the inner structure of the inner part of the star system looks like. That basically the yellow cores of these of the images we just saw, we now zoom in even farther to a smaller scale, and we have the cartoon version of the inner disk and the star forming accreting material out of the disk.
Right. So like I said previously, the magnetic fields of these young stars are so strong. And so this is like the picture of what I was describing, that the magnetic field lines are weaving into the disk, and then they're locked in with the disk. But where they are connected to the disk, there's material that flows along the magnetic field lines, and they can actually hit the star and cause essentially a big explosion, and can increase the brightness of the system by hundreds of times. And that's called an accretion hotspot. And this may be one of the processes that contribute to disk dissipation. So that's one of them. And then another process that can contribute to disk dissipation is flare activity, or other, and like the winds can, stellar winds can blow the disk away, or it can photo evaporate. So there's a lot of different theories right now about how the disk we know it eventually goes away. So how it does that, accretion, as shown in this image, could be one of those things.
So we have another question from Chris Georgie saying that there's there must be a very high shear zone at the boundary between the magnetically locked region and the freely rotating region out beyond that, which I guess that's another area where people are modeling, how viscous the disk is, and then where the disk is locked on the inner part.
Absolutely. Yeah. There's a lot of turbulence in that region. And actually there's even a lot of turbulence going on in the inner parts of the disk, where it's not transparent optically, but we could image that in, say, longer wavelengths. We do see that in like the very, like where it says disk on the image, there's a lot of turbulence going on there as well, in addition to the shear, where it transitions from it's called the co-rotation regime or area on the inner edge of the disk to the non-co-rotating part. So
all of this activity must mean that there's quite a lot of variability in the brightness of the system.
Yeah.
I think you have some good illustrations of that.
I do. Are you referring to the light curves, Brian?
Yeah.
Okay. So I'm going to show that. I'm going to exit out first. Oops. Well, actually, here's this actually does show the different contributions of brightness. So we could start here, and then we can show what a light curve might look like.
Sure.
So this is an image showing different types of magnetic activity that can occur in these systems. And so here we have, like, on the left side, the label of accretion flows. That's what we were just talking about. And then the hot spots that occur at the foot of the accretion stream, that like big explosion of shocked hot gas, can really brighten the system tremendously. But then young stars have really cold spots, like the sun. The sun has them also. However, these cold spots are extremely large. They can take up like tens of degrees across the face of the star. And then they are also very long lasting. And so this would change the brightness of the system as the star rotates. When the spots come into view, the total brightness decreases. And when they exit from view, the total brightness increases. Or you could have a hot spot occurring at the same time. And while the brightness is decreasing, it could suddenly increase. And brightness is also attributed to flares too. So you could have flares going off several times an Earth day, and as well as prominences. And so all of these things contribute to the total brightness of the system, which compared to the sun looks very chaotic. And so now I will show what one of these light curves might look like in a different slide.
So we need to be go back to the full screen mode ultimately.
Yes, we will do that. So let's see. I will show a light curve. Let's see, which one would be the best? How about, we'll just go through like a sequence of what a star might look like with a disk, and then without a disk, and if we were trying to look for a planet around that. And like how the total brightness might affect that kind of thing. So if we look at a main sequence star, we have the brightness versus time. You can see that there's kind of like a periodic wave going through the light curve. But then there's these dips that happen every X amount of days. That's pretty consistent, and that's a planet transit. The planet is passing in front of the star, decreasing the system brightness, and when it leaves the face of the star, the brightness goes back up. So it's fairly easy to detect planets around older main sequence stars. If we were to look for this around a young star, there's a little bit more going on. However, this one doesn't have a disk, so it's not including any accretion. or like accretion hotspots, like those explosions. It doesn't have any of that, but even without those, we see that for this young star without a disk, that there's still a lot going on. And we can sometimes detect a planet around something like this. However, so this is what the brightness over time of a system would look like if it had a disk. And so that really complex system of the artist rendition we were looking at really, I think, is really highlighted in this light curve in the upper right. And that's because we see there's not like really a clear periodic signature that might be from like rotation or planet transit. We know that there's actually a planet around the star, but it's not transiting, so we wouldn't see that here.
So this was the sorry to interrupt. This was the planet candidate that was found by Lisa's group here at Lowell.
Yes, yeah. So this is the young star Ci Tau, and it does host a hot Jupiter. If we want to, we can actually head back to that slide. Brian, what do you think?
Sure, why not?
Okay. Sounds good. I will.
While you're doing that, I'll mention a couple of questions here. One from Jim Davies: would the turbulence in the disk help to form planets? And I think the answer is people are still pondering that, and whether turbulence prevents things from accreting into things like planets, or whether it actually causes things to run together to actually form the larger chunks of stuff out of the gas and the dust. Mm-hmm. And then Chris Georgie again asking, does the co-rotation regime migrate inward or outward as the system evolves? And I think the answer is it certainly does. And we'd like to have more details about that sort of process.
Absolutely. Yeah. I imagine it would also, depending on the evolution of the magnetic field, that might be a contributing factor to that.
Right. Yeah, I'm sure there's several different processes that we try to untangle and to see how it gets so tangled up. So here's our Ci Tau planet candidate.
Yes. So we have on the left an image of Ci Tau. This is taken with ALMA. And we see here that it has several rings also. So we know that it hosts a hot Jupiter, but it may also host 3 other planets in addition to the hot Jupiter. And here we have an artist's rendition of that. So this was from a press release on the research that presented the image on the left. And so there are at least several Saturn mass or more planets that would be carving out the gaps in the disk here. And that's really cool, because this is the youngest planets that have been detected to date. And then 2, this is the system with the youngest system with the most planet mass detected.
Okay.
Most total planet mass. And so we know that these planets can form at these ages, even while the disk is present, or while the disk is in the process of evolving. So
the easiest thing that we could, the actual original detection was with presumably the innermost of these planet candidates. Is that the case?
Mm-hmm. Yeah.
So we have this, idea that I guess as the stars are forming, the planets are forming at the same time, and that there's some complex interaction between where the planets are, I guess, on the inner part of the disk, these ones that are easy to detect on the inner edge of the disk, and then possible other more distant planets that would be much more difficult to detect. And maybe some of those are either getting thrown into the star or ejected, these big planets getting thrown out in some cases.
And those are the extreme cases. Oftentimes, we found that planets might be just migrating somewhere in the disk. They might form where they don't end up necessarily. So they could form further out and then migrate inward through disk interactions and also interactions with other bodies in the system. And so they could end up really far in, but formed really far out. And so that's another mystery. That process is a mystery that we're trying to solve.
So, I mean, I guess I was going to, having to do, you were showing the light curve, this very complex light curve of Ci tau, and a few minutes ago, and I'll mention that you have done some work on trying to extract signals from of the rotation of the star and the effect of the planet spinning around hidden in that data.
Mm-hmm. Yes. So although it might have seemed like there was no way we could detect a planet in that light curve, what we have found is that we might be able to detect planets that are interacting with the disk that are creating those really sporadic looking signatures. And so the innermost planet of this system, the hot Jupiter, we found is interacting with the accreting material. And so as when the material accretes onto the star, it causes that hot spot that increases the system brightness as it comes into view. And so the brightness is dependent on the rate of accretion, or how much mass over time is falling onto the star. And so the planet will change how much mass over time is falling into the star. And then so as the planet orbits, we are detecting that brightness change on the timescale of the planet's orbit rather than the star's rotation, because we would expect it to be the star's rotation if it's locked with the disk within the co-rotation radius, right? So if there's a planet there and we detect an accretion signature that isn't on the timescale of the star's rotation, then it should be from another source. And so the periodic signature that we got from the light curve that was indicative of accretion that wasn't on the timescale of the rotation had the same period as was detected initially with the planet. And so that is why we think that the planet is the source of that the planet is pulsing accretion effectively onto the surface of the star, which is changing its brightness on the timescale of the orbit rather than the rotation.
So we had a question from Kent Kolbath, who's asked basically exactly a related question, which is, wouldn't you need the radial velocity curve to detect the planet that's not transiting rather than the light curve? And indeed, in the case of Ci tau, the first planet was in fact identified from the radial velocity change that was different than the period of that radial velocity change was different from the rotation period that we could see in the ordinary visible light. We had both data from Lowell, both the photometry and also the radial velocity data from several telescopes, I think, that showed the existence of the planet at a different period. That was the key item. Mm-hmm. So obviously these things are quite complex, and there's quite a lot of work still to be done, mathematical processes to be able to try to extract these some kind of systematic signal from a very chaotic, what looks like very chaotic pattern. So I guess you had, of your light curves, you had another one that I saw earlier where you had actually been able to extract out, I guess, was it from Ci tau or another one, that you were able to extract out these multiple periodic signals?
Yeah, so I can go to that one. I will escape and head over to that one here. Okay, so this is K2 light curve of Ci tau. So K2 is the follow-up mission to the Kepler mission that was intended to stare at a single part of the sky for years. And it was successful at that until its reactor wheels, two of them had failed, making it so that it was no longer able to maintain the level of stability that it would need to. And so we were able to repurpose the Kepler telescope for a new mission called K2, where they actually use light pressure from the sun to stabilize the telescope. Really creative, and I'm really glad that it was solved because now it enabled us to get these data here. And
Good
so this
engineering.
is the light curve.
Good engineering success.
Yeah, absolutely. Definitely a success story. So on the left is the light curve of CI tau, and on the right is called a periodogram. And so the y-axis says power, and then the x-axis says period. And power is essentially just like the strength of a periodic signal that would occur in data that would look like a light curve, for example. And then the period is what period are we analyzing? So there are a couple primary periods that we had detected. We know that the stellar rotation is about 6.5 days. And then the planet orbital period that was initially detected with radial velocity is 9 days. And again, it's not transiting. So we know that this isn't from a transit. There's not some small signal hidden in the light curve that could be from that. And so that's also why we think that it's interacting with the accretion stream, is because that is something that would come into view. And it would make sense that it would interact with the disk and change the rate of accretion. So this is what the light curve would look like for CI tau.
And so we think having this long string of data that went for, I guess it goes for almost 3 months, continuous on CI tau, allowed us to do a much better job of identifying these periods than we could do from the ground, at least in the terms of the brightness change of the star. Because we'd actually seen the 6.5 days with photometry that we had done measuring the brightness of the star from the ground, but the nightly cadence and cloudy nights and so on made that a little bit uncertain. And so we were able to, it says Biddle et al. 2018, we're able to confirm this in the K2 data, where we have a continuous string of data, no cloudy nights in the K2 data. So we have another question, which is the periodogram essentially the Fourier transform of the curve?
Absolutely, yes, it is the Fourier transform, except it's actually quite nice in this case because it allows for uneven sampling, whereas with a Fourier transform, it's required that the data are sampled evenly in this case time. But that's not always the case, even though the light curve itself might look like the data are evenly sampled, and that would be ideal. The telescope does go through adjustments during the period of time that it's observing. It'll like roll, or sometimes you'll just get reduction routine will flag up a point that says, actually, this was happening during one of like the more technical maneuverings. And so that creates a bigger gap in the observing cadence, and that is not ideal for Fourier transform. So that's why we use Lom-Scargill to create the periodogram on the right.
So yes, there's a lot of mathematical analysis that goes into these data to try to extract something meaningful from them. So clearly, we're Lauren and the rest of the folks in Lisa Prato's group are working on these various problems and trying to parse out when the planets form and how they get there, and how the stars form too, and at least small parts of these questions that we have about how the universe gets here and going in the first place. So I guess we can probably wind things up here now. Thank you for doing this, Lauren. And hopefully we can have you on again when we have another big breakthrough.
I would love that.
And I'll mention that for folks watching, that you can subscribe to the YouTube channel for Lowell Observatory and get notifications of these Cosmic Coffee presentations on the Thursday mornings, and also other events such as the remote virtual observing that we do on Tuesday nights, and other things that we have going on online. And so thank you for doing that. We'll be back again next week. Not sure exactly what will happen, but we'll be back again at the same time next Thursday morning, and hope to see you then. So thank you, Lauren, and thanks to our technical crew behind the scenes here, and we'll sign off for now.